Nature is nonlinear. Nature is mechanics. Nature is composite. Nature is structured. In short, nature is the dance of nonlinear mechanics of composite structures. प्रकृति गैर रैखिक है, प्रकृति यांत्रिकी है, प्रकृति समग्र है, प्रकृति संरचित है. संक्षेप में प्रकृति समग्र संरचनाओं के गैर रैखिक यांत्रिकी का नृत्य है. भूमिमंगलम भूमिमंगलम उदकमंगलम उदकमंगलम अग्निमंगलम अग्निमंगलम वायुमंगलम वायुमंगलम गगनमंगलम गगनमंगलम सूर्यमंगलम सूर्यमंगलम चंद्रमंगलम चंद्रमंगलम जगतमंगलम जगतमंगलम जीवमंगलम जीवमंगलम देहमंगलम देहमंगलम मनोमंगलम मनोमंगलम आत्ममंगलम आत्ममंगलम भूमिमंगलम उदकमंगलम अग्निमंगलम वायुमंगलम गगनमंगलम सूर्यमंगलम चंद्रमंगलम जगतमंगलम जीवमंगलम देहमंगलम मनोमंगलम आत्ममंगलम सर्वमंगलम भवतु 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 सर्वमंगलम भवतु 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 सर्वमंगलम भवतु भवतु भवतु.
Very good morning to all of you. Are you able to see the slide?
Yes, sir.
Okay, thank you. Yeah, in the previous class, we looked at one of the gentlemen who is responsible for this particular course in terms of the content, primarily the textbook that we are going to follow, Nonlinear Composite Beam Theory, Professor Dewey Hodges of Georgia Tech. In today's class, we will look at his mentor who happened to give us this variational asymptotic method onto which the mathematical basis of this is built upon. Though most of us see this variational asymptotic method as purely a mathematical tool or technique to accomplish a lot of things, not only in structural mechanics, but fluid mechanics, and pretty much every engineering problem where you have a variational principle, which is what the V in VAM stands for, which is governed by a variational principle, either directly or through a weak form, and which is pretty much most engineering problems in any case. And then you are able to identify certain small parameters in the very problem definition, either from the geometry or from the whatever is the physics involved or the science involved with that particular process. And that again, the presence of small parameters is kind of omnipresent in engineering. Any engineering problem you take up, you will see that there are situations where you can very easily identify small parameters. So that's the essence of the A in the VAM, that is the asymptotic nature of the variational asymptotic method. And therefore, though we all see it primarily as a mathematical technique, Professor Berdychevsky himself takes a lot of pride in looking at this as a physical interpretation of whatever mechanics has usually been in the previous centuries, that is, let's say the 18th, 19th centuries. Mostly the mechanics was mathematical in nature. If you take some of the classical treatises that are there, like by Love, etc., you would see that it's highly involved in mathematics. One of the great books, which also you can use as a reference, is Ogden's Nonlinear Deformations, and that again is written by a mathematician, Professor Ogden. So the beauty that Professor Berdichevsky brings into all this is the physical aspects, and to correlate the mathematics with the physicality. Because once you go too much into abstract mathematics, it becomes different from an engineering approach. It's more of a mathematician's approach. And that's the reason why many engineering departments like our own, the aerospace department, have started teaching their own mathematics courses to bring the students up to a certain level in the mathematical techniques, which are essential from an engineering point of view rather than a mathematician's point of view. Still, a lot of the abstract concepts from mathematics continue to be of great relevance, and that's where the engineering applications or applied mathematics stems from. So theoretical mathematics is indeed important, but for a practicing engineer or for those who are concerned only with engineering problems, even if it's a research in nature, then it's the applied math which becomes significant, and therefore we should not lose the touch with the physicality. And that's essentially what Berdychevsky likes to be referred to himself as somebody who is more into the physical interpretations of the various aspects of variational principles or mechanics, thermodynamics, fluid mechanics, many different areas that he has been involved with. And it wouldn't be afar if I say that in my interactions over the last 3-4 decades with so many great people from the scientific and engineering field, I find a lot of people who are really good at being in depth about their subjects, but do not have the breadth. And similarly, I find a lot of people, equal number probably, who are very good at their breadth in understanding the bigger picture, working a lot on multidisciplinary optimization, design problems, etc. But they have no depth in one particular field that one can that a big community can actually look up to. So this is essentially the uniqueness of Professor Berdychevsky. In the interactions that I have had with him, I have recognized that he is one of the very rare persons who is very deep in whatever he has produced in terms of the body of knowledge through his teachings, through his papers, through his monographs like the one that you see on the screen right now. And at the same time, he has the breadth of understanding of what math, physics, science and life itself is, and therefore puts everything into perspective. And that's what makes the beauty of it all, so that anything that we get from his sources, be it books or papers, is something that appeals to the inner sense in us and can stay with us for much longer than something just to be memorized, written in an exam or in a paper and then forgotten about. So that's essentially the beauty of this gentleman. And the reference book that I'd like all of you to at least peek through some of the important sections, because it's a vast set of 2 volumes that are there and covers various aspects, so many of which may not be directly relevant to our course over here, but as and when it's necessary, especially the variational asymptotic method part, it will be good to hear it from the horse's mouth. And that's another thing, that message that Professor Berdychevsky has always passed. Whenever students write papers, they tend to whatever they have gone through a reference, they tend to cite it without noting that there could have been the same work which was done in a much more fundamental way much earlier. So it's usually the first work that is should be given the most importance, and we should not forget to cite those breakthrough papers which were the ones which led to those papers from which we are getting the knowledge. So always giving credit to the original value adders. See, everything, as I said, is a discovery rather than an invention, but some discoveries, the value addition is far more. And so that if we can go down in our search and research to understand those aspects which are the ones from which many other things that we use on a regular basis are actually developed from, that original paper or original book or original source of knowledge is what is to be given the most credit to. And also there are other things that I've learned from him, more like an ékalavyā, because I've never been his student, but at a particular conference, one of my juniors from Georgia Tech was having a discussion with him, and I happened to overhear what he was advising. And this person had written some papers. He was very enthusiastic, and he's somebody who's published rampantly, and after that particular meeting. But what I would like to emphasize here is, because many of you you are going to be writing your paper as part of this course, a technical paper which is going to be published in a journal for the first time. So these philosophical aspects, if learned early on, are very, very important, because ethics is what really governs the reputation. And Professor Berdychevsky, some of you who know the VAM literature may have guessed which student, which junior of mine here, Professor Berdichevsky, was talking to at that point of time. I do not want to reveal that name. But Professor Berdichevsky was telling this person who was going ahead with publications, he told him, if you lose anything in life, you can get it back, be it health, wealth, even your intelligence. But if you lose your reputation, you can never ever get it back. So it's very important to maintain that ethics upfront, and that, which is why I would like all of you to utilize some of the tools that IASC provides to you, like Turnitin, which is a plagiarism check software that all IASC students have access to, and then Grammarly, because as much as what you do in terms of a scientific or mathematical or engineering contribution is important, how you communicate it is also equally important, and which is why I have three modes of communication put into place in the grading of your research as part of this course. One is the video, because the video is becoming yesterday's paper. What were typically given in the form of papers earlier on, slowly are getting into videos, and people are more accessible, and especially the younger generation looks forward to the videos more than reading a paper, and therefore the ability to convey a large chunk of work which you have worked on for hours on end over many weeks, which you are putting in, let's say about 10 pages, you are putting in 2 minutes of a video, and therefore the ability to convey that succinct information. In this context, again, you might recollect what I mentioned about Bernard Shaw's advice to one of his admirers, saying that if you need to talk about your lifetime achievements in 1 hour, you speak slowly, because the amount of achievements that we have had, however great we are really, really small. In Tamil, there's a proverb, "Therindadu kaiyalavu, theriyadadu kadalalavu." That means what you know is just a handful, what you do not know is as big as the entire ocean. So, or even for that matter, katrathu kaiyalavu, katradadu kadalalavu, which means that what you have learned is also a handful, what you haven't learned or what you do not know is much, much bigger. It's infinite compared to the infinitesimal knowledge that we all have. And this is why Professor Hodges also, one of his advices has been to many students that if you don't know, it's okay. If you don't know that you don't know, then there is a problem. Many people are arrogant about their knowledge without recognizing how small it is, and that's when you're not open to getting new knowledge. That's why they say you have to be like an open box, but there is no box itself, so why even bother about opening it? Recognize that there is no box, and then you would see that you would be open to knowledge from different sources. It's not that you just absorb everything. You know, you have the intelligence to reflect upon it and absorb what is essential, and then apply to your specific problems of the day, whatever is relevant. That is the usual approach that you have to take. So these are tiny tidbits that I give, but these will come in really handy when you are going to write this paper. As you know, this Friday the abstract is due, the draft abstract, which, as I said, is more like a sankalpa, and therefore writing that is very, very important, because that was going to kind of dictate how your paper paper is going to flower. It's more like a bud, the abstract, and then it starts flowering. And so that bud is very, very important. So do spend sufficient time to do that. And you have two wonderful mentors, one Kaja, who's experienced with variational asymptotic method and the geometrically exact shell theory, applying it to a very complicated problem of membranes wrinkling. So you have his resource for understanding the technical aspects. And in terms of actual publication and the applications that are involved, Professor Vinyas Mahesh is a really amazing person, an youngster whom you can relate to because of the lesser age difference. And then you can see, you can get a lot of tidbits from him in terms of how you can approach working on your research in the first place, and writing and communicating that in various forms as well. I'll probably arrange for a talk by Professor Vinyas Mahesh sometime so that you can get an understanding of the approaches which are kind of state of the art in terms of how you define a problem, how you approach it, and how you try to resolve it. What is the motivation? What is the practical motivation? And therefore how you eventually convey it to a wider audience that you would like to cater to. Always keep that audience in mind also. So whenever you're giving a talk, like the 30-minute presentation that you're giving, or the video that you're going to make, or the paper that you're going to write, you should have an idea of what is the background and what's the kind of people who are going to be absorbing your knowledge, and therefore you have to tailor the way you communicate to be accessible to them and to be of utility to them so that they can take it forward as well. So that is essentially the approach that we are going to see. So this VAM reference that you see over here is a 2-volume set, as I said, which is titled as the Variational Principles of Continuum Mechanics that you see over here by Professor Victor Berdychevsky. The first volume talks about the fundamentals, and the second volume talks about the applications. And this is, as I said in the previous case, it's about the book by Professor Hodges was part of a series which is the Progress in Aeronautics and Astronautics of the American Institute of Aeronautics and Astronautics. On the other hand, this is from Springer, and it's again a part of a series which is the series called, which has many books, Interaction of Mechanics and Mathematics. And that's where Professor Berdychevsky is the ultimate in terms of very deep understanding of both, because he has PhDs in both. So he's a double PhD, a particular kind of doctorate which is not commonly known of in various other countries, even Western countries like the US. So he has that training of research in both math as well as science, which in particular mechanics, of which thermodynamics is a subset, the way he comes out with it. And mechanics includes both solid mechanics, what we are going to focus on in this course, and the fluid mechanics or gas dynamics as well. So this is a book, the previous book was 2006, which is our textbook. This one is 2009 from a Springer publication. So please take a look at it, especially the a small section related to the variational asymptotic method, which will be of great utility in your research work. So just like I gave you an idea of the gentleman behind this whole thing, I would like to do so with the case of Professor Berdychevsky as well. I had the opportunity of catching up with him in various conferences. This one that you see over here is in Germany, where the gentleman in between is the one from whom I learned all of my little bit of knowledge on composites. So he taught me my very first composites course, Professor Arian Armanios. He's an Egyptian. See the beauty of all this. I talked about in the previous class a Brazilian who was my mentor, Professor Hodges himself, an American, who was my PhD advisor, Professor Berdychevsky, who was a Russian, and Arian Armanios, who's an Egyptian. So the kind of knowledge which comes to us from various sources, from various geographies, becomes so significant in terms of understanding that it's the same science and math that we're all talking about. That's the common language. Just like music, it might have various genres like Carnatic, Hindustani, rock, jazz, whatever. But you see that the basic build-up is the 7 tones that you have, or the saptaswaras, and therefore everything germinates from that single source. In that sense, knowledge sharing across people is very, very significant, which is why I travel a lot, at least before the COVID, in terms of international conferences, having presented at almost 40-45 countries, and interacted with people from various backgrounds, to be open in mind to the knowledge that comes from various sources. But at the end of the day, the basic fundamentals remains the same. So let me talk a little bit about Professor Hodges. We had an opportunity, all 3 of us, to catch up once, in fact 2 or 3 times. Professor Berdichevsky and Professor Hodges. You see, this is Berdychevsky, this is Hodges, and this is me without a beard at that point of time. And it was an amazing meeting. And this is the meeting that I'm going to talk to you about in a little more detail, because this was a celebration of the 65th birthday of Professor Berdychevsky, who you see with family over here. And this is me. This is Professor Hodges, and this is Professor Arian Armanios, and this is one of the Russian friend couples of Professor Berdichevsky and his and their family, grandchildren. So you see that this was a conference in his honor, and about less than 50 to 100 of us got together, his students and grand students, etc. And then we discussed various works of his, and which followed later on through his students and grand students. And it was a really wonderful conference. This was sometime in the last about 12-13 years back, and that was a precursor to the conference that I hosted for Professor Hodges, for Professor Hodges' 70th birthday. So this is 65th birthday of Professor Berdychevsky, where at that point of time Professor Hodges was just about 61, and there was after this conference, once again a special issue of a journal was released in honor of Professor Berdychevsky, what we call as a Festschrift, or Festival of Schrift, that is writing. And that special issue, unlike the previous one of or the one that I talked about on Thursday or Wednesday last week, was in the AAA journal. This was in the International Journal of Engineering Sciences, and this appeared in honor of Professor Victor L. Berdychevsky, which was the Festschrift celebrating his 65th birthday. Victor, the L in the middle name stands for Lvovich. So Victor Lvovich Berdychevsky was born on June the 28th, 1944. Professor Hodges' birthday is in May, the very next month, the birthday of Professor Berdychevsky. And he was born in 1944, which is near the end of the Second World War. As many of you know, the last World War, and hopefully that we have ever had. And Professor Berdychevsky was born in Moscow, Russia, and as you know, Russia was deeply involved in the World War as well, the Second World War in particular, and therefore Professor Berdychevsky was named in honor of the anticipated victory, Russians' anticipated victory for their grouping, and therefore his first name, Berdychevsky of course is his family name, or his last name, and his given name is Victor, which means that they were anticipating victory and therefore named him as the Victor, because he was born during that time. So, and the reason why they were so involved with that war is because his father fought at the Western Front, being a member of the infantry unit, which was formed by the, very interesting, these days we think we are so distinctly apart from the military forces, that the infantry unit that his father was a part of was actually formed by the graduates of the best university in Russia at that point of time, and a great university even today, Moscow State University. So Moscow State University graduates got together to form an infantry unit which was part of the the Second World War, and his father was a part of it. So obviously his father was not a professional soldier. He was an academician himself as well. In fact, his father was a biologist, and his mother was more closer to what he does today. She was an engineer, and this engineer biologist couple had this child in 1944, and he has a brother as well, and Victor often jokes in his own words. I mean, his jokes are really short and sweet, and with the Russian accent that he speaks, the punch is even more. So in his words, he used to say that he and his younger brother, just two children to his parents, so he and his younger brother received a lasting vaccination, which is significant from today, the COVID-19 vaccines going on of the double doses all around. So Victor used to joke that he and his younger brother received a lasting vaccination in their childhood itself, as most of us do, by their parents' love. So love is the best vaccination that we can give our children, and that can actually take care of various issues and problems that we encounter in life, be it scientific and technological or anything else for that matter. So in life, whether it is health issues or wealth issues or knowledge issues, they all can be vaccinated through true love, which is basically the recognition that we are the creators of our own destiny, in the sense that whatever we have done in the past is what we are facing right now, and therefore the love, caring and sharing that you have for the entire life, not just humanity but all of life, is something that automatically gives you all these ethics. Then you don't need to learn caring, sharing, love and peace and all these separately. Those come as collateral benefits automatically if you understand who you really are, who we really are. So in 1961, that's about when he was 17 years old, Victor became a student at the university at where his parents were teaching biology and engineering. So in 1961, at the age of 17, Professor Berdychevsky, who was going to become Professor Berdichevsky, Victor just then, became a student of the same great university called Moscow State University, which I already, as I told you, was ranked number 1 in Russia, and at that time, it was the home to some of the amazing scientists and engineers who are kind of people who are not celebrated as much as our French or British or American scientists and engineers, just because most of their work was in Russia, and USSR, as you know, at that point of time, was kind of a closed entity, like how North Korea is today. And we never had much of information flowing out of it. But later on, now when we see things that they had published in the 70s and 80s, some of the mathematical mechanics papers are like such breakthroughs that have not even been done, let's say 30, 40, 50 years, half a century later, by Western scientists and engineers, so, or anywhere in the world for that matter. So and that's the amazing abilities of the some of the top Russian mathematicians and mechanicians, and many of them were alive and were actively teaching at the Moscow State University at that point when 17-year-old Victor went to school over there. And it was at that time, as I said, some of these scientists' names you may not have unfortunately heard of them, but if you have the time and the interest, I would strongly suggest that you research into some of these names. One is Kolmogorov, a great mathematician and mechanician, Landau, Arnold, and Professor Berdychevsky's own advisor Sedov. These are the kind of output that they have come up with. It's really amazing. And many of us have grown in our engineering mathematics also with Pushkinov and many other great mathematicians from Russia. So we know what they are capable of. As I said, is Professor Victor Berdychevsky's research advisor right from the undergraduate days, not only for his master's and PhD, but even for his undergraduate project and for the courses that he took as part of his bachelor's degree, was Eli Sedov. And you can see where all that genius comes from. As we do in the Indian tradition, this is this Guru Parampara that we have, and we eventually offer it all. So whatever little that I know, Hodges knows, or Berdychevsky knows, eventually goes to Sedov and his masters as well. So Victor obtained the Master of Science degree with the highest honors, not surprising, in applied mathematics and mechanics. As I said, these are his two strengths. So his master's itself was in both of them. And this was in 1966. So he was about 22 years old. So 5 years after he went into his undergraduate, he had his master's degree as well. So just a year for his master's. And obviously it was from the School of Mathematics and Mechanics at the Moscow State University. And he received his PhD degree in 1970 from the same school, Moscow State University. In the West and in Russia too, we typically call engineering or even universities typically has departments. What we call in India, we call them as schools in most of these Western countries. So the PhD degree in 1970, so he was about 26 years old when he received his first doctorate, and from the same school again, Moscow State University in 1970. And in 1982, much later, that is almost, he was 38 years old, he received the Doctor of Science degree, what we call as DSc, Doctor of Science degree, which has no equivalent, as I said, in the West, including in the US. And this second degree was from the Institute of Problems in Mechanics, and this is not a university degree, it is from the Russian Academy of Science, Moscow. So it's unlike the fellowships that we have of various professional bodies today. I talked about Professor Hodges having 4 fellowships from 4 top academies of professional bodies in the US. Similarly, this is something different from that fellowship. It's more, that is more of a honor commemorating the huge body of knowledge that they have produced, but this is part of a learning process, the education, the Doctor of Science, and he got it from the Institute of Problems in Mechanics. So the importance is, see, we have to be a part of the solution rather than the problem, but unless we understand the problem, we can't seek the solution for that problem. So that's why the problem definition is so important, and that's why I was urging many of you in our one-to-one emails last week when you were coming up with the title, because that title, even though it is a tentative title, it conveys the problem. It's kind of a problem definition up front in the most in the shortest way that you can have. What is the problem that you're going to attack? Is it a really important problem? Is it a significant problem? Is it a problem that others haven't looked at? Or if they have looked at, are there better ways in which we can look at? Are there faster ways in which we can look at? Are there less expensive ways in which we can look at? So that all that is becomes as part of your abstract, which you're going to put now in the form of your sankalpa, which is due this Friday. So Professor Berdichevsky got his second degree at the age of 38 from the Institute of Problems in Mechanics of the Russian Academy of Science, Moscow, Russia. And after graduation from 1970 to 89, that's almost 19 years, Professor Berdychevsky worked in Russia itself before he came to the US. For these 19 years, 1970 1970 to 1989 were amazingly productive years in terms of the variational asymptotic method, which came out. And this book, as I said, is written in 2009, but this is just an English version, a much upgraded version, of course, giving a lot more details. But the original book original monograph was written in Russia during this period when he was an academician in Russia itself for 19 years, from 1970 to 1989. And Victor worked in the department of hydrodynamics. That's where all of his fluid mechanics and his works in turbulence in recent years have shot from, probably the training that he had in hydrodynamics. Hydro meaning water, and therefore the dynamics of water flow. As you know, steam engines and hydropower plants, electricity being produced by hydroelectric projects were all very, very significant at that point of time, and therefore hydrodynamics was a great body of study at that point of time. So this was a separate department dedicated to hydrodynamics in the Moscow State University, where he started from his undergraduate all the way up to 1989. So that is when he was almost 45 years old. So he went there at 17, and till 45 years he was with Moscow State University, one of the best universities around the world. And this department of hydrodynamics that he worked in from 1970 to 89 was a part of the School of Mechanics and Mathematics, where he studied in various other departments as well. And this department of hydrodynamics was headed by his advisor right from undergraduate. So for all these decades, he's been with Professor L.I. Sedov, and you can see the kind of depth and breadth that he has acquired. The source of that is Sedov, and Professor Berdichevsky has a lot to say about those years and the amazing things that he learned as part of that training. Even as a faculty member for 19 years, he continued to benefit from his collaborations with Professor Sedov, who was the head of the department at that point of time. And in 1989, the various issues, as you know, Gorbachev being the president of the USSR and the chancellor, and then all the agitations and things that took place, domestic issues of USSR, which broke apart into various countries, of which Russia was one part. And then many great scientists, engineers, emigrated out of the Russian or the Soviet states, the various Soviet countries that they became, including Russia. And one of them was Professor Berdychevsky, to the benefit of America. Some of them went to various Western European countries as well. A similar thing happened during the Second World War also. As you know, many great people like Einstein moved out of Germany, Hitler's Germany, and into the US and other Western European nations for greater freedom, because it's in freedom, and that's the beauty of an academician's job. There's a lot of academic freedom, which is of course a double-edged sword. You can either use it or misuse it. Unfortunately, many misuse it. But the academic freedom is something which helps us germinate and nurture and grow all the way from a sapling to from the seed and sapling all the way to a plant and a tree, the bodies of knowledge that we want to spread out, and through the fruits to the students and their students, and so on and so forth, and through collaboration through our partners and so on. So in 1989 he really desired that freedom, which was kind of becoming a constraint that the way Russia was being governed at that point of time. So the socio-politics plays such an important role. This is something that you need to understand. That though we are students or academicians, we are not disconnected from the rest of the nation, and the socio-politics, the economics of the nation and of the world, the global economy, or the global village as we call it today, are so very significant in whatever we do, because that has to eventually get into that economy, into that humanity, whatever benefits that we can probably provide in a small way. So in 1989, Professor Victor Berdychevsky and his family, they moved from Russia to the United States, and he became a professor in the university where I did my PhD. He was a professor in the School of Aerospace Engineering there at Georgia Institute of Technology, which is known as Georgia Tech for short, where he met Professor Hodges, who had just arrived 5 years prior to that, after working for a very long period of time in the NASA and US Army and Stanford. So then he had come to Georgia Tech, and 5 years later, somebody was 4 years senior to him, Professor Berdichevsky, comes in, and just through a chat over lunch or a dinner, amazing things came out of it. So these informal talks that we have with colleagues, with peers, with students, with our mentors, these can sometimes lead to amazing breakthroughs, and that's the kind of partnership which eventually ensued between Professor Berdichevsky and Professor Hodges that I benefited from, and many of my students who are now faculty members across the world in many of the IITs and the American and European universities. Those students, I didn't read the full paper last time, but if you look at the last 1/3 of it, it would talk about various contributors to that, and you would see that 9 of my students have written papers as part of the issue honoring the Festschrift AWA Journal special issue honoring Professor Hodges. So that's the beauty of it. Just like in a family, we have this academic family where we have our students as like our children, and our students as our grandchildren, great grandchildren, and so on, various generations of academicians. And it's amazing when we meet up at conferences, etc., and recollect the way our knowledge and wisdom has developed over the years, and how we each of us is contributing, and we never forget the roots from which we came. As I said, Professor Berdychevsky became a faculty member at Georgia Tech in 1989, and he worked there only for 5 years, 89 to 94. Very unfortunate for me, because he left just the month before I went to Georgia Tech in 1994. I went in September. He probably left in August or a little earlier than that. So I missed meeting him there, but all of the knowledge transfer had already taken place to Professor Hodges. So Professor Hodges and his variational asymptotic method body of knowledge was all derived from Professor Berdichevsky, and I could benefit from that and have later on taught it to many of my students, some of who are a part of this class as well. So from 1994, when he left Georgia Tech, almost like 27 years now, he's been a professor in the mechanical engineering department at Wayne State University. So he moved from aerospace, first from mechanics and mathematics, hydrodynamics in Russia, to aerospace in Georgia Tech, and to mechanical engineering in Wayne State University, where he spent almost 3 decades of his career now. So he's been a professor in the mechanical engineering department, as I said, of Wayne State University, which is in Detroit, Michigan, in the US. And over the years, Victor's research activities spread over many areas of mechanics, thermodynamics, statistical mechanics. This plays a very, very crucial role. I used to have a really wonderful professor in IIT Madras, Professor Balakrishnan, who used to teach statistical mechanics as part of the basic physics. We had physics 1, physics 2, and physics 3 in 3 semesters, and the 3rd semester physics was so engrossing, and maybe it's part of some of the NPTEL lectures as well. You can search for Professor Balakrishnan and see that the statistical mechanics plays such an important role, because most of us keep working on these deterministic methods and methodologies, which are good to understand the basics, but eventually you see that most things in life are having a certain random nature to that. Random because we do not understand what they are. But if you look at the geometry, if you look at SEMs, spectral electron microscopic images of various composites, if you look at the images of the core of sandwich structures, not honeycomb, which anyway from the macro scale, from our naked eye, we can see that it has a certain geometry, which is more regular in nature. But if you look at foam, or any polymer for that matter, or even crystalline materials, even single crystal materials like nickel-based single crystal materials, which are used in the high temperature applications like turbine blades of aircraft engines. Even there, you would see that in the aircraft engine turbine blades, the material which is used to withstand such very high temperatures at the rear end, because it's the air has already burned the fuel and is coming out as an exhaust, which is very, very hot, and at very high speed it's getting accelerated through the nozzle at the end, and therefore the materials you need there typically single crystal materials, but even there is so much of randomness in their basic structure. And some of the very recent works of Professor Berdychevsky in the last 4 or 5 years has been more towards understanding these the randomness processes in single crystal materials as well, which will be of great significance to those of you who may work on metal matrix composites and eventually take forward to a lot of these engine applications, or even applications like Gaganyaan is going to be launched through a vehicle which is going to be capable of re-entry. So you have to see in that re-entry the kind of aerodynamic heating which takes place, and the kind of materials that you need over there. And in many of them, statistical mechanics will play a very, very critical role. But even in the understanding of the regular polymer matrix composites and or even metals, whether it's in the polycrystalline or single crystal forms, single crystals being typically more higher performance and also higher in costs because of the more intricate manufacturing techniques that are involved in making them. So in all of these, statistical mechanics plays a very critical role, and Professor Balakrishna's lectures at IIT Madras on this was so engrossing that he had a huge fan following. Typically for these subjects, basic subjects like math, physics, chemistry, we used to have multiple batches. Those days it was just about 250 undergrads at each IIT. That's all that we had. So we had about 5 batches of 50 students each, and each batch had its own physics teacher. But for this physics 3, you would see that the students of the other batches are all bunking their classes and coming to Professor Balakrishna's lecture, because that was the level of engrossment. And we had it in a huge lecture theater. It used to be filled, and there used to be people peeping from the windows and doors to listen on to him. So that's the kind of fan followings which not just sportsmen or sportswomen and film actors have, but some of these scientists, engineers, and academicians have too, which is really amazing for the thirst of knowledge that these students have. And that thirst is very, very important if we want to accomplish something of even some small utility to humanity before we leave this planet from this particular form that we have. So over the years, as I said, Victor's research activities have spread between mechanics, thermodynamics, statistical mechanics, which I was just discussing, and also applied mathematics. And that's where bringing in the physicality of the mathematics is where he really shines. And even over a coffee, I don't drink coffee, but over a coffee, when we have discussions with Professor Berdychevsky, I've had the opportunity of one-on-one discussions with him. It's just amazing what kind of things that he talks. Absolutely unanticipated nuggets of knowledge come out, each of which can become a body of knowledge that huge groups of students can work on for their entire, not only their academic careers, but their entire professional careers as well. So let me give you a brief list of the accomplishments of Professor Berdychevsky. In the mid-1960s, when he was still in Russia, in the Moscow State University, he developed, in collaboration with his mentor, Professor Sedov, right from the undergrad days it was Sedov, and in collaboration with Professor Sedov, Professor Berdychevsky developed a dynamical continuum theory of dislocations. And I'm very happy to see that his great-grand student, that is my student, Professor P.J. Guru Prasad in IIT Mumbai, IIT Bombay, he works on these dislocations and plasticity related problems, etc. And this is where it all comes from. And Sedov and Berdychevsky together developed this dynamical continuum theory, which is kind of still, it's almost been 60 years since they developed it. It's still kind of the gold standard for understanding dislocations. Dislocations are basically the failures that happen because of something getting dislocated. Even your bone fracture, for example, if you have through an accident, etc., it's basically a dislocation that could happen, let's say even of the joints, etc., and you know what kind of issues that leads to. Similarly, any material that is part of the aircraft wing or fuselage, if it undergoes due to unanticipated loads or loads over a period of time, it undergoes certain dislocations. How you can understand that using a continuum process, because dislocation, remember, happens at a very low length scale. In the case of fiber matrix composites, it could be of the order of the fiber diameter, which is of the order of a few microns, which you can visualize only through SEMs or such other ND techniques where you can evaluate what is going on, not just at a given point of time, but as the situation worsens with the crack growth, etc. So these dislocations become bigger and bigger. In other words, from the original point of the location where it was intended to be, it has moved away, drifted away to quite some extent, creating probably voids or cracks and things like that. So all of these things are typically understood at a lower length scale. But how to understand it from a continuum mechanics point of view is what the dynamical theory that Berdichevsky and Sedov developed on the dynamics of it. That is how it actually evolves, how the damage, in particular dislocation, how it evolves is what they came up with. And as further developments in the same field showed, their work turned out to be the first, and it was a pioneering work. And these pioneering works are what you have to seek in each one of your papers. You have chosen really interesting topics, the 10 or 11 of you who are, it's a good cricket team that we have. So you have very nice batting and bowling coaches in Vinyas Mahesh and Sheikh Bipari Muhammad Khaja Moinuddin, and you have a coach like me, like Ravi Shastri is for the Indian team, and therefore utilize all of our resources, and you have chosen really wonderful projects, almost like the IPL, and make it flower and come to fruition. So and in doing that, you have to look at the literature survey to start with, and that literature survey always go to that pioneering work, that first work which was done, which was a breakthrough work which led to that entire body of knowledge. And without mentioning that in the literature survey, your paper is not doing real justice to that field, because it is ignoring somebody who has made the germinal contribution to this whole thing, who kind of sowed the seed for this entire tree of that particular area of research to flower up. So please make it a point to search backwards to the root. Of course, you should do a lot of state-of-the-art literature survey so that you can say what is the current state of that literature, or that's the body of knowledge, and therefore what is the gap that is there which you think you can fulfill by your new unique kind of approach at solving the same problem. So that is identification of the research gap and how you would tend to fulfill that research gap. But never forget to at least give a mention to that first body of knowledge from which this entire field in which you're going to work, not the broad field, but the more specific field that your topic or title is in, that field, which was the, and it may not be just one, there might be 2 or 3, probably even sometimes some rare cases, a dozen such pioneering works, many of which might have happened independently also, especially in those days when the communications were not so rapid and were in different languages. People could have just as a coincidence been working on similar problems or working on different problems, but came up with some collateral benefits which happened to be very similar in nature in terms of the new understandings that they brought about. So this particular work on dislocations of Berdychevsky under the mentorship of Sadov. So the real credit goes to Berdychevsky, though the mentorship is of Sadov. It showed that in this particular field, their work turned out to be the first pioneering work that is in the area of so-called strain gradient plasticity. Some of you who are exposed to plasticity might know about the gradients that are there in the strain and how that affects the plastic behavior of the material and therefore of the structure which is made out of such a plastic material. By plastic material we mean even the metals which go into the large strain regime and into the in the stress strain curve, there's a region beyond the elastic limit which is plastic in nature, and that is the region where this understanding of strain gradient plasticity, which has become a huge body of knowledge, lot of journal papers, many different journals, books, research monographs, thesis, PhD thesis, and many sub-departments of various engineering departments have been focusing as big teams on strain gradient plasticity, and the source of it all was the work by Berdychevsky with Sadov, and which in fact, and the strain gradient plasticity didn't become a body of knowledge for 20 years after this breakthrough by Berdychevsky and Sadov. That's something that we academicians do, and sometimes we feel frustrated that even though we think our work has been so awesome, amazing, breakthrough, it doesn't seem to be impress many other people. But if you look at history, not only this particular case of Sadov and Berdychevsky's work coming to a new body of knowledge called strain gradient plasticity 20 years later, many other cases also you would see that academicians typically are working on very futuristic problems and taking a lot of risk. If they work on 10 problems, maybe one or two might succeed. The others go waste, and those one or two also many a times it doesn't become so popular and easily adapted by the rest of the community. But you see, like 10-20 years down the line, you see a lot of people are seeing the benefit of it. Usually pioneering academicians like Hodges or Berdychevsky, Sadov, etc. are very futuristic in their approach, and that's what a faculty member, many of you who are doing PhDs might be looking at academic careers in the future. So you should know that we academicians typically work on futuristic problems, taking a lot of risk, and therefore don't get frustrated when your work is not appreciated or utilized by many people, not cited by many people. So citations typically for some of the most pioneering works have picked up decades after their original publication or their coming to light in the first place. So that's precisely what happened in this case of the strain gradient plasticity as a fallout of the continuum theory of dislocations of Berdychevsky and Sadov as well. Then again in Russia in the mid 70s, and I was a small child at that point of time. He had got his degrees prior to I was born. So in the mid 1970s, he developed a direct method, Professor Berdychevsky. He developed a direct method for what is very, very important that we are going to study over here. And what is that direct method? For asymptotic analysis. And asymptotic analysis is basically you have an exact theory or exact solution which is difficult to achieve either analytically, numerically you may approach it, but it's kind of time consuming. But even for that numerical approach, you need an approach which is computationally efficient. So essentially what you're trying to do is to approach that exact solution which is not possible in other means. The next best is to reach it in an asymptotic sense, which means in terms of the small parameters that you have identified. So many of you, for your papers, we're going to, or your research, you're going to apply the variational asymptotic method. Then the first thing, as I said already, is to identify what is the governing variational principle. So it's not the formulation like in Newtonian mechanics where you have governing differential equations, but if you have it only in that form. There are ways to convert that set of governing differential equation into a variational principle. So that is the first step, to identify that variational principle which you're going to use for your problem. Then second thing that you will do is to identify in the problem definition itself what are the small parameters. So this is what will help you to apply the variational asymptotic method, and this is what Professor Berdychevsky did almost half a century back. So in the mid 1970s, he developed this direct method, and this direct method was for the asymptotic analysis of functionals. So rather than because asymptotic analysis or asymptotic approaches were not new, even before Professor Berdychevsky there were many other people who were applying asymptotics, but the difference is all the asymptotics which were applied on problems of science earlier, or any problem for that matter, the asymptotic approach was always towards the differential equations or governing equations, be it algebraic, differential, integral, or combinations of those. But essentially for those boundary value or initial value problems, what people were applying were asymptotics at the equation level. But the thing is that when you are applying it to equations, if it's a single equation which is governing a problem, a simple problem, then applying asymptotics at that leads you to amazing results, very useful results, hugely improving your computational efficiency without sacrificing your accuracy. But if you apply it to any realistic problem which is governed not by a single equation but by multiple integro-differential algebraic equations, including boundary conditions, initial conditions, constraints, etc., and some of the constraints being equality constraints, inequality constraints, greater than or less than, or greater than or equal to, or less than or equal to, these kinds of constraints you have. And so these are fairly complicated problem which is not governed by a single equation, and therefore if you start applying asymptotics to this, because these are all coupled set of equations, these are not independent equations, some of them might be independent, but essentially at least two of them are coupled with each other, and you dropping higher order terms in one of the equations will adversely affect the other equation, and that might not lead to an asymptotically correct solution. So you've lost that beauty. So on the other hand, the functional approach or the calculus of variations approach, what it does is it takes you back to the very stationary principle, which is the basic principle of from nature, which governs that entire behavior of that material or that structure, be it in solid, fluid, gaseous form, whatever, or combinations of those, be it in mechanics or thermodynamics or any other field, electromagnetism, etc. The essential thing is that if you go to the fundamental principle governing it, there is just a single entity which is the functional. Yes, you might have the constraints also, but you can include those constraints along with the functional by using Lagrange multipliers, etc. With inequality constraints is another approach that you can have. But essentially what you're doing is that you are boiling it all down to a single functional that whose stationary value you want to determine, and what are the functions which arrive at that particular stationary value for that functional, and that becomes the solution for your problem. So in the mid 1970s, that's almost half a century ago, Professor Berdychevsky independently, and this was without the direct guidance of Professor Sedov, for the theory on continuum dislocations, he worked with Sedov, but for this he was still working in the department for which Sedov was the HOD, but it was an independent contribution from him. Professor Berdychevsky, one of the things that we value the most, because that's what we correlate to a lot, but many of his other contributions are equally great, or if not greater. So in the so at that point of time, 50 years ago, he developed a direct method for the asymptotic analysis of functionals, and as I said, which depend on small parameters. That's why the asymptotics is possible. And as I said, almost every engineering problem, you name it, will have certain small parameters. It may not have a variational principle governing it. Some of the dissipative mechanisms like damping or friction or viscosity in the case of fluid mechanics, etc. But you can arrive at weak formulations, the closest functional that you can fit to, again in an asymptotic sense, and then you can start with that functional and then arrive at solutions which are very, very useful in an engineering sense, because they are both accurate as well as computationally extremely efficient, and can be used especially for structural health monitoring, for detailed design, and for accident investigations, failure analysis, improving the designs through optimization studies, etc., where you need to do a lot of iterative number crunching. Each time you save 50, 60, 70, 80, 90% of that CPU time, you can see the huge benefits you have in taking your product to the market much, much faster, solving issues that are there in your existing products through an analysis much more quickly, and therefore rectifying the issues and reissuing the second version or the new version of the product. All of these can happen amazingly in a much, much better sense. So this method, which is now called, he didn't call it the variational asymptotic method at that point of time. It's just, and he never gave his name to it. See, we never say it is like Hamiltonian principle or Lagrangian principle, Maupertuis principle, which was the very first variational principle, by the way. Most people don't even know about Maupertuis. But they were all given the names of the people who actually came up with those. But Berdychevsky never wanted that name and fame, and he never called it as Berdychevsky variational principle or whatever. So this, and he and even the variational asymptotic method name came up much later, and this method is now called as the variational asymptotic method, and it has been applied, thanks to Professor Hodges especially, to a wide range of mechanical problems. And he himself has applied it to quite a few problems in his single author papers, to the development of improved theories of elastic plates and shells, which is basically a superset of plates, beams, which again are engineering structures of great relevance, as you know, not only in aerospace but in many, almost all other branches of engineering as well. And the theory of high frequency vibrations. See, the initial works were all for statics or low frequency vibrations, so the dynamics was not so critical over there. But once you go to high frequency dynamics, I explained to you in the very first or second class when a student asked a very interesting question, why wavelength? So as I said, when high frequency vibration comes, high frequency means low wavelength, because frequency and wavelength are correlated with each other in an inverse sense, and therefore a high frequency vibration, or where the dynamics is very critical, or it cannot be treated as a static or quasi-static problem. In such high frequency problems, so what you're dealing with is not the actual length but the wavelength, whether it is of a beam or for that matter of a plate. So you instead of dealing with the actual width and length of the plate, you are actually dealing with the wavelengths of deformation. So if it's undergoing certain dominant modes of vibration, what is that wavelength? With respect to that, you have to compare the thickness, and in this case the thickness is very large compared to the wavelength, and therefore you can't treat it as a dimensionally reduced structure. But there might be small parameters coming from the physics of the material. This material, this says skin or the bones inside, might have a certain level of strain that they can have. The skin might not have a very low strain. It can probably stretch much more. But the bones, the amount of maximum strain they can go to before dislocations or fractures occur is fairly small. So they are typically ceramic in nature. So you would see that it's a brittle fracture that would occur over there, and therefore the small strain capability of that material can become the small parameter with which you're working. So there are no assumptions involved here. It's just from the very physics, the behavior of the material, the actual construction of this structure, the geometry of that structure, the typical frequencies at which it is vibrating, normally in a typical loading situation. These are the things that dictate which are the small parameters. No assumptions are made over there, and therefore that is the power of this method. The reason for its accuracy is because all of the simplifications in the mathematical governing equations, be it integro-partial differential equations, nonlinear in nature, involving certain integrals, involving certain integral, non-integral constraints, equality, inequality constraints, whatever they might be, they are all going to essentially boil down to much simpler formulations purely because of the existence of these small parameters which you need to identify. So that is essentially these two aspects that you have to look at, apart from, of course, writing the abstract as a sankalpa, the literature survey, which is very critical, as I said, going all the way up to the pioneering work in that field, as well as covering the most recent state of the art so that you don't miss them and then come up with something which somebody else has published just a few months back or 1 year back, and you think yours is completely new, but just because you didn't look at that paper, or even if you have looked at and unethically said that yours is original work, it gets found out very easily these days. Plagiarism checks is the first thing that editors will perform on your submission of a manuscript, so there's no escape to it. And even if somehow for some reason you escape, and eventually later it comes to the knowledge of others that there is a plagiarism involved, as I already told you about Professor Berdychevsky's suggestion to one of my juniors, if you lose your reputation, you can never ever get it back. Unfortunately, some of our great scientists in the recent past have lost that reputation because of the plagiarism done, maybe not by themselves, but at least one of their teammates or co-authors have done that, and they overlooked it, and that's the kind of issues that they can fall into. So because you're working with us, and we value these ethics quite a lot, be it Kaja or Vinyas or me, and therefore I really plead with you that you come up with something that is really original and unique. And also when you even in the literature survey, in your introduction section, when you describe your paper, make sure you do it all in your own words. It is a description of somebody else's work, but still you're not taking verbatim the material from there, because that gets very easily detected by plagiarism checks. And even if it is not detected, you are not true to your conscience, and therefore you can't have pride in your work, which is one of the collateral benefits that you get out of doing a really good piece of work. And therefore I really plead with you that give a lot of important significance to the ethical aspects and the way you communicate in your own words. You read up something and then you write it on your own. So that is very, very essential. So continuing with the contributions of Professor Berdychevsky, one is of course the statics and low frequency dynamics, then the high frequency dynamics theory, which one of his students, Professor Lei, in Ruhr University Bochum in Germany, further developed, and there's a book he has written on vibration of rods and shells by Lei. Is a Vietnamese direct student of Professor Berdichevsky, unlike me, more of an ékalavyā. So this direct student has written a monograph, which is also an amazing book. I used to teach a course on the theory of plates and shells, high frequency dynamics, about 20 years back, based out of that book. And again, amazing mathematics and mechanics in that book as well. And he has covered high frequency problems very well, because this is a very difficult problem, because once high frequency comes in, low wavelength, and therefore one of these small parameters that you are taking advantage of, namely the cross-sectional dimension to the length, and now is no longer a small parameter, because the length has become the wavelength, which is much smaller, or of the same order of magnitude as the cross-section, or maybe a little bigger than that. But so you lose out that advantage. But as I said, you have many other small parameters you have to deal with. So it's usually a complicated problem to deal with high frequency dynamics, and even more so with impact mechanics and such other problems. So there you have to look at some of these few works that have been done in the small body of literature that is available, applying variation asymptotic methods to such high frequency problems. And Lei is one name that really comes to my mind on this. But Berdychevsky himself has done a lot of work, and that's how Lei as a student could develop it further. And Again, the high frequency vibration problem has been applied to regular isotropic materials, also to piezoelectric materials. Piezoelectric, as you know, piezo means pressure and electric is the electric field. So a coupling between the mechanics and the electrical energy. So the mechanical strain energy and the electrical energy having a transfer between them. So not only for conventional materials, but also for piezoelectric materials, both even high frequency problems. Kanchaulet has done some work, which again was based on the original work which was done by Berdichevsky, which were unfortunately all in Russian and very, very crisp and short papers. Many steps missed out in the derivations, like our Srinivasan Ramanujan, the great mathematician from India who went to Professor Hardy in UK, and the kind of works that he came up with also, there are a lot of missing steps because these are geniuses that just know the next step without having to go through a step-by-step derivation, just go on doing it because of the flow of knowledge that they receive from the very source of life. And when you have that kind of an approach, it becomes a little difficult to understand. So Kanchaulet's works are a little more accessible than Berdychevsky's original works in Russian. And Berdychevsky continued working on many other problems as well. Some examples, so the high frequency was applications were for plate, shells and beams. Then he also did, Berdychevsky himself did some work on the homogenization of composite materials, but he didn't take it too far. He left Georgia Tech at that point of time. Ashraf Badir was one of his students, whose PhD thesis I benefited a lot from. That was one of the first PhD theses that I read before I came up with my own research. So he later worked with Professor Arian Armanios, who taught me the composites course. And then this homogenization of composite materials, Professor Berdychevsky worked in two different ways, and one of the ways has not been extensively used, and that's something that many of you can look forward to using in your future careers as well. The periodic kind of microstructure most people have already dealt with, but it's the random microstructure, and that is the reality. The random microstructure, be it a composite or be it any non-composite material, also the microstructures even in single crystal materials are so random in nature, and to understand the probabilistic characteristics of that geometry, that has been done very well in terms of the SEM images and things like that. People know the probabilistic characteristics over there, but how does that probabilistic characteristic of the original geometry of this single crystal material or polycrystal material or the composite or the polymer, how does that translate towards the behavior of the structure that we make out of it? Let's say an aircraft itself, or a wing or a tail. That's a big gap. Just knowing at the fundamental level, it doesn't mean that you know at the structural level as well. The building blocks are all known, but putting together is not a very simple thing because they're all nonlinear building blocks and principle of superposition doesn't work. So you have to work from scratch over there. And that's why his work on random microstructures is very important, because the way, see again, randomness or probabilistic methods or stochastic methods, a lot of people have worked on these problems. But what we are looking at over here is to understand it from a much more fundamental perspective, not through wild number crunching. Just because we have great hardware and software today doesn't mean you go through donkey work and let your computers or clusters or cloud computational networks do these donkey works as well. There are much more refined, easier ways of doing things and arriving at almost as accurate results. So Monte Carlo simulations, for example, a lot of people get into for stochastic methods or probabilistic methods is absolutely unessential in many problems, because you can understand it from a much more fundamental level, even though it is random or having certain probabilistic characteristics and the model is nonlinear. Still you can arrive at solutions, both analytical as well as numerical, which are much more fundamental in nature and much more of value in terms of repeated applications, where time savings apart from being accurate are equally important, and therefore therefore you can achieve far more in a shorter time than what others can. So he has done a lot of work not only on periodic microstructures but also random microstructures as well. And as I said, he's worked on problems involving fluid flows in porous media. Dr. M.R. Bhatt, with whom Nilesh, one of your classmates, works, has done a lot of work on understanding voids and pores in composites from an experimental approach. But there's also a lot that can be done in a theoretical sense. And in porous media, Professor Berdichevsky has done a lot of work in terms of fluid flow through that porous media. What really happens? For example, it's very important in understanding agriculture and things like that, or even water retention. Why we lose out on all the water. India gets so much of rainfall through the monsoons, etc. But still, so many regions which still are in drought, etc. River networking and things like that will work to a certain extent. But what is essential is that retention of the water in the locations where the rainfall is there, instead of letting it all go away into the ocean. Okay, so that how you can actually handle that is through that flow in the porous media, which is the soil. And there the topsoil plays such a very, very important and critical role. And how you retain in it the beauty of that mathematics, physics involved there, and the engineering, which evolution has taught the trees to do it automatically. By the way the tree roots are there, it makes sure that the seepage of the water is not as much, and the water retention in the soil is much more, even well past the monsoon season. And therefore even throughout the year, perennially, you can grow multiple crops and things like that. So that is essentially what is the porous media flow. There's another colleague of mine who used to be in IISc till recently, who moved on to IIT Gandhinagar, who used to work on the porous materials as well. But Professor Berdychevsky long back has gone into fluid flows in porous media. It's a very, very complicated problem, involves the fluid mechanics, the porous media's solid mechanics, and the elasticity and plasticity that might be involved, the change in characteristics as it becomes wetter and wetter. So in other words, the hygrothermal stresses which build up, and then the retention and the flow, all these things are, and the temperature dependence, the thermodynamics which is involved over there. So all these complicated problems can be handled with the variational asymptotic method. So that's the kind of powerful tool that you're going to deal with in this course in a practical sense, because many of you are going to apply it for your actual chosen problem, the title that you have already given to me, and the abstract that you're going to write by this Friday. So you're going to actually apply this all-powerful method to this particular problem. So make sure that you are well trained for it, because you have to do a lot of self-study and reading apart from what I teach you in the class as well, to be able to accomplish this. Because this is like giving a surgeon's knife, what is called as a scalpel, in the hands of a child who can hurt himself or herself. So this is a very, very crucial, important, powerful tool that you're having, the variational asymptotic method. So use it wisely and use it for a purpose that your title ensures, and the abstract as a sankalpa does. That's the reason why the sankalpa is so very important, that you take this sankalpa or abstract right up front, so you know what you're going to use it for. You're focused on that topic and you're not wavering around, because you have a deadline as well. Within a few weeks, you're going to submit various aspects of this, in terms of the video, in terms of the presentation, in terms of the final manuscript. And therefore, to accomplish this in a timely manner and still come up with something which is which you are proud of throughout your careers, as this is going to be your first paper, and something which is going to be of great utility and value for the society going forward. Because many of the problems that you have chosen, I'm really happy. There's a wide range of diversity that is there in terms of the choice of problems, and almost all of these problems, luckily, you have chosen are of great societal relevance, things which either in the engineering industry or even beyond that. For some of you, it's a medical related problems, etc., that you have chosen are really, really very, very impactful problems. And that's where the motivation for a lot of our research should come. Not just because I can do it, I do it kind of a thing, but to foresee, to perceive where what I do will probably fit into. Of course, it might fit into many more things which you haven't even thought, but at least something that motivates you. Yes, this particular application my work can actually go for, and so therefore I'm self-motivated to do that. Nobody else keeps to come and keep pushing you. Kaja doesn't need to push you, Vinyas doesn't need to push you, I don't need to push you. You can do it by yourself because you are motivated by that particular problem that you're going to solve. And if you solve that, how impactful it will be and how helpful it will be for a large class of the society, and therefore you're doing it all by yourself. So that's essentially what I would like you to get on to. Continuing with the contributions of Professor Berdychevsky, apart from the high frequency vibration problems of composite materials, he's worked on nonlinear dynamics problems and wave propagation problems. One of you is looking at wave mechanics, so you can look at the search for wave propagation related works of Professor Berdychevsky to see if that can be one of your starting points. So the idea is to identify the variational principles governing wave propagation and then take it forward. So I already explained to you in very great detail in the email that I reply that I sent to that particular student who has chosen that problem. And to each one of you who have asked relevant questions related to your choice of topics, I have had the pleasure of replying to you in terms of certain leads in terms of how you can go about it. But eventually it's going to be your baby. I'm just a midwife. All three of us are midwives who are going to assist you in this through your pregnancy, through your labor pains, and eventually the delivery of the baby. But you are the one who is pregnant with this idea, and you're going to you have conceived it as a title. Now you're getting it into the form of a fetus as part of this abstract, the sankalpa, and then eventually it's going to grow all by itself through your own efforts, and then self-efforts and self-motivation, and then let's see how it actually is born, and how that child eventually becomes useful for the society. So that's essentially, as a mother for your paper, for your research, and for your manuscript, you're going to make a huge contribution. So make sure you do it in a way that a typical pregnant mother would do. So that's the kind of approach you take towards your manuscript, and even before that, the research itself which leads to that manuscript. So in fact, it was established later, continuing with Professor Berdychevsky's contributions, it was established much later, in fact, that almost all well-known asymptotic methods, I mentioned Maupertuis, I mentioned Lagrangian, I mentioned Hamiltonian, and there are many others as well. Okay, in Professor Berdychevsky's book you will see all that, because he doesn't want to avoid giving credit to whoever has worked on something which eventually he has come up with. So it was established later, however, that almost all of those well-known asymptotic methods, not only variational principles but the asymptotic methods, which were applied to differential equations earlier but not to functionals, those asymptotic methods, all the well-known asymptotic methods for that matter, in the field of mechanics in general, and even more general physics, such as those of Lindstedt-Poincaré method, many of you might have heard of. So the Lindstedt-Poincaré asymptotic approach, there is the Bogolyubov-Mitropolsky approach, which is basically a Russian approach that I doubt many of you have heard of. And this third one, very significant work, Kolmogorov, Arnold and Moser approach to asymptotic methods. Again, unfortunately, not very well known outside Russia, but it's a fundamental work. And then VAM's work. All of these four and many more asymptotic approaches, asymptotic analysis methodologies are all actually derivable from the variational asymptotic method. So if you know the variational asymptotic method, many of those become special cases. So those special cases are much easier to deal with later on. Like I have been telling you, if you understand composites in a certain sense, of course, including not only polymer matrix, but metal matrix and ceramic matrix composites, you can deal with isotropic materials as well, metals and ceramics and polymers automatically. So it becomes a special case. If you understand nonlinear approaches to problems, you can do linear problems very easily. So as a subset. Similarly, if you understand the variational asymptotic method, other asymptotic techniques of all of these great people prior to Berdychevsky can also be treated as special cases. They can be derived from that. And same thing with the geometrically exact beam theory of Professor Hodges that I talked about in the previous class. That becomes like a superset out of which you can see that many other theories being the higher, either the classical theories like the Euler-Bernoulli beam theory, or in the case of plates and shells, the whatever Kirchhoff-Love theory you have, and for beams you go one order higher in the shear deformations to the Timoshenko theory, or in plates and shells you go one order higher to the Reisner-Mindlin theory, and many people who have made a living through higher order shear deformation theories both for beams and plates and shells. Absolutely no need for all that. If you know these geometrically exact theories, all of that can be obtained as special cases using the variational asymptotic method by just going to the next higher order approximation. And there's absolutely nothing new in many of those, though they have made a living through a lot of papers and books by just publishing these incremental improvements in their own theories or their others' theories. So VAM and GBT, therefore, and also GST are all very, very fundamental methodologies from which many others can be treated as special cases. So we are really lucky to have this particular knowledge from these two great gentlemen, Professor Hodges, whom I discussed in the previous class, and Professor Berdichevsky, whom I discussed in today's class. And of course, their combination, because the more recently the variational asymptotic method has been used as a basis for developing numerical codes like the variational asymptotic beam section analysis called as VABS, VABS, and VAPS, variational asymptotic plate and shell analysis, VAPAS, and VAMUCH, variational asymptotic homogenization approaches, unit cell for the unit cells that are there. So this is basically for the micromechanics approach. And there's something called the structure genome kind of an approach. But essentially, all of these works have already been done in the 70s and 80s by Berdychevsky. It's just taking tidbits of that and making it in a more presentable form, in an engineer-friendly form. People can more have it in a more accessible way. That is all that many of us have been doing over the years. So the VAM has been used as a basis for developing numerical codes, whereas my approach has been more towards analytical sense, as I explained in the previous class as well. But we do look at certain numerical implementations as well for realistic structures where the geometries and material distributions are so complicated that we can't afford analytical techniques. But in between there is also a semi-analytical approach where we try to push the extremes of the capabilities of analytical techniques to have a little bit of numerical and analytical and to get certain. And the reason why analytical or semi-analytical approaches are so important is it gives a lot of insight into the physics, much more than what a numerical approach can give. Yes, from the numerical approach through processing, you can get a lot of these insights as well. But you directly get, by just looking at an equation, you fall in love with it and you know how things are affecting each other, the sensitivity and all that, without even having to solve that equation or to get numerical data out of it, or plot graphs out of it, 2D or 3D graphs out of it, color graphs, etc. Without doing all that, just the equations can give us a high, can get us intoxicated, and a lot of physical and mathematical insights that we can get into these things. And these codes like VABS in particular have been employed based on, of course, the VAM, which was developed by Professor Berdychevsky, and its implementation by Professor Carlos Sesnik, as a PhD student of Professor Hodges, my mentor from Brazil, as I said. He was the one who first came up with VABs. There are many versions of it later on in the last 20-30 years. And these codes, where like VABs, are employed extensively by the aerospace industry, in particular the helicopter industry, by Boeing helicopters, that is, which of course took over McDonnell Douglas helicopters, which were one of the leading helicopter companies in the past. So Boeing, which includes McDonnell Douglas today, or for the last couple of decades, and then Sikorsky, a person from Russia, just like Berdychevsky, who moved to the US and started the Sikorsky helicopters, and which is one of the leading helicopter companies today around the world. Sikorsky uses VABs. Then US National Labs, they use VABs. Bell helicopters, with which I have collaborated a lot, both in the US as well as in Canada, they use VABs, and we've done a lot of things beyond VABs also for Bell helicopters, working at NMCAD lab. And in the mid 1970s, Professor Berdychevsky began a series of works concerned with the homogenization of periodic and random structures. So this is again still in Russia. So most of his seminal works, which kind of led to seeds and saplings and plants and trees and flowers and fruits, which all of us are benefiting from, were all done 30-40 years back in Russia. And so this work on random structures and periodic structures, how to homogenize them, coming up with an equivalent homogenized imaginary material which behaves in a macro sense similar to the original material, whether with or without damage. That's something he had a paper in 1975 itself. Of course, it was in Russian. If you translate it into English, it would be spatial averaging of periodic structures. The word used for homogenization by him in the equivalent Russian at that time translates to spatial averaging. So you're averaging in space, or kala. And kala in our Indian culture refers to both space and time. And therefore, you have space-time finite element analysis, where you're discretizing not only in a spatial sense, be it 3D, 2D, or 1D finite elements, but also bringing in the fourth dimension of time, and you're discretizing in time as well, which is very useful for a lot of dynamics problems, including impact and fatigue problems, high-frequency dynamics problems, both through free vibration or forced vibration, etc. But in all of that, the building block would be this homogenization, what he called in 1975, Berdychevsky called in 1975 as spatial averaging. So spatial averaging of periodic structures. So he started with periodic structures and later on realized that periodic structures don't have much relevance in reality, and therefore moved on to random structures. So, but the 1975 work on homogenizing periodic structures was actually again a pioneering work, just like the plasticity work. Remember I told you about the strain gradient plasticity body of knowledge that his continuum mechanics of dislocations led to. Same way, this work on his work on the spatial averaging of these materials, that is periodic structures, actually led to a huge body of knowledge as well, because it was the first where the variational cell problems for averaged Lagrangian or periodic structures was formulated. So this average Lagrangian approach, where you use a Lagrangian approach, you are familiar with two kinds of approaches: a Lagrangian, which is typically used in the solid mechanics, and Eulerian, which is used in fluid mechanics, but it can be used the other way also, depending upon what one is used to, but predominantly that's been the approach. But in the Lagrangian, there's an average Lagrangian approach, and for that the variational cell problem, that is each cell that you have, there is a variational approach to that, a problem definition based on that. For that, this became a pioneering work. So, and this was of course for periodic structures to start with, and the formulation is based on that 1975 work by Berdichevsky, and therefore it wouldn't be afar if we can say that Professor Victor L. Berdychevsky belongs together with some of the greats like Bakvalov from Russia, Lyons. So there's some great Greek scientists also who worked on this, like Papanikolaou, Kozlov, Bensosan, and all of these pioneers actually, and Berdychevsky is one of them, pioneers of the homogenization method, that is going to a material which is an imaginary material, not the real material, but something that you can use to do things much faster, and then have say about the actual real structure, which is kind of useful as well. So these are all the pioneers of homogenization method, which is, as you know, some of your classmates actually who are not crediting the course, but who are unregistered guests like Renuka, etc., and Khaja himself, are applying to many problems nowadays in many areas of mechanics, nanomechanics, etc., wrinkling in the case of Khaja, and all of these, the source is the 1975 paper on periodic structures, which essentially led to the understanding of homogenization from a very fundamental mathematics and physics point of view. I'll just take another 5 minutes, probably less than that. Professor Berdichevsky obtained a number of new exact solutions. That's where my love for him is much more, because of the analytical approaches that he also takes sometimes. So he obtained a number of new exact solutions of homogenization problems, including computation of local fields, because you want to eventually come back to the reality and what is happening in the localized regions, right? Local fields in chessboard structures. So if you know a chess board, it has 8 by 8 black and white alternating. You know how the geometric configuration of that is. So if you have a unit cell and then you build a representative volume element based on such a unit cell, which Renuka is very familiar with, you can see that you can get the effective moduli. The effective moduli of elastic materials, isotropic or anisotropic, but in this case, Professor Berdychevsky's original work was for elastic incompressible composites, because many of these are with Poisson's ratio hitting for isotropic materials 0.5, as you know, is the upper limit, and which means that the material is rubber-like or close to being incompressible. So for such elastic incompressible materials, there's a material constraint which is coming from that. So how do you get the effective elastic moduli for those materials? And all of that can be done very easily by using this original approach of Professor Berdychevsky, where he estimates the effective moduli of random structures as well going forward in terms of that of periodic ones, because the periodic structure, whatever he had, the random structure, he looked at it as a building block. The periodic structure model was the building block for the random structure, and he put many of these different property periodic structures in a random configuration, and therefore it comes up with this, again in an analytical sense, for exact solutions. That's the beauty of it all. So estimates the effective moduli of random structures in terms of that those periodic ones. Later on, he obtained one of the central results of the in the homogenization of random structures, which is the formulation of the homogenization problem in terms of probability density functions. So probability density functions, or PDFs, as you know, are very, very critical in many different kinds of probability distributions that you have, be it Gaussian or non-Gaussian, and therefore that becomes the starting point for the material understanding, and then you use that to understand the structure. So you are building up from the micro model of this structure to the of the material, to the micro model of the material, to the material itself at a macro level, level, and then the structure built out of that material at the beam or shell or stiffened monocoque semi-monocoque structures that you might have. So the result, this result of Professor Berdychevsky first appeared in his paper in 1987, just 2 years before he moved to the US. And that paper, again, the English translation of the Russian is available. And I think the English titles go something like The Problems of Averaging Random Structures, because you're averaging from the periodic structures. So, and it's in terms of the distribution functions, which are the probability density functions that you have. And this was further developed in his monograph. So apart from this monograph that you see on the slide over here, that is Variational Principles of Continuum Mechanics, 2 volume 1, he had one more monograph earlier on, which was called something related to these the thermodynamics of chaos and such kind of things as well. So but you would see a lot of this work on the periodic and random structure homogenization also in this particular book that you see on the slide as well. As I said, this is going to be our reference book, at least for the VAM portion of it, and has become a modern classic. See, you usually refer to something as a classic or a legend if it's long back and still has value. But these are some of the living legends with us, both Hodges and Berdychevsky, and we need to take advantage of that. So it's worth noting that a number of results in this particular book, 2009 book that you see on the slide over here, actually first appeared in the Russian edition in 1983 itself. That is almost 26 years before this book came out. So in that quarter century it took for translation and also bringing in some of the missing blocks, as I said, many equations with missing steps, and also an introductory section where he actually says, very interestingly, the first chapter, according to an advice that he got from one of his mentors, was that it should be written in such a way that undergrads should be able to understand this. So the first 30 pages of any book that you write should be something that even undergrads should be able to understand. So keep this in mind when you write your manuscript also. The introductory section that you write, somebody who's not exposed to that area, they should also be able to relate to what is the problem that you're trying to handle, at least in the introduction section. And of course, you'll lose many of them as you go forward, more and more intricate into your research. But at least the beginning, you should have the ability to capture the audience. As even Einstein say, you should be able to, or Newton said, you should be able to explain what you're doing even to your grandmother, who may not have a exposure to the kind of body of knowledge that you are working on. So anybody not exposed to that body of knowledge should be able to understand. That is the whole point, at least in the basic structure of it, the problem definition, the abstract, the introduction. These are things that everybody should be able to understand. So we should typically write it in that way. But even though this is a 1983 work put in English in 2009 with a lot of additions, it still looks so fresh, showcasing the genius that Professor Berdychevsky was and is. And in the mid-80s, Victor produced a series of works on thermodynamics and statistical mechanics, both of which are related very closely, intricately to mechanics. Most people don't realize that, and thanks to Professor Balakrishnan of IIT Madras, I realized that quite early on. And so thermodynamics was one of my favorite subjects. Unfortunately, I haven't had the opportunity to work on it much, but Spalding and Cole is the textbook I remember reading on almost every one of my train journeys between Chennai and Bangalore for my vacations. Not a second lost of those journeys. Everything was spent on Spalding and Cole, falling in love with every equation there and every line of text over there describing those equations and their derivations. So Professor Berdychevsky developed thermodynamics and statistical mechanics of finite dimensional ergodic Hamiltonian systems. So we will go through some of these terminology like ergodic and Hamiltonian later on in the course, because ergodic means you can see from the very etymology of this word, it's derived from the two Greek words which are ergon, which means work. You say ergonomics, your sitting posture or your standing posture, all of these have to be as conducive to your health as possible. So that is essentially ergon. Ergon means work in Greek, and hodos, not hodges, hodos means is a Greek word which means way. So it's the way of the work. So ergodic is derived from the Greek words which mean work and way. So ergodic basically means that you are relating to or denoting the because it's an adjective. When you say something is ergodic, for example, we are saying here that it is a ergodic Hamiltonian system. A Hamiltonian system is governed by Hamilton's stationary principle, the principle of variations, where you need to find the stationary value of a quantity or a functional, which you call as the Hamiltonian. So if you say that Hamiltonian system is ergodic, what you mean is that it is relating to or denoting systems or processes with the property that given sufficient amount of time, they include or impinge on all points in a given space. So for example, in the space that this aircraft is, all the points on the aircraft, both on the surface as well as within, you are able to say what is the state of stress, state of strain, etc. And these can be represented in a statistical way. And by a reasonable large selection of points. So that is how many points, minimum number of points you need to describe it in a reasonably accurate way. That is the whole trick. And that's where the transition from periodic analysis to a random analysis actually helps. So in particular, Professor Berdychevsky obtained an exact formula which was linking the probability and entropy. Again, entropy is a very, very interesting concept that many of you would have explored through thermodynamics. You had a course, the MTech students had a course on the mechanics and thermodynamics of propulsion in the previous class, and entropy is something which keeps increasing for typical processes, real life processes. So it behaves in a very different way from energy that we are more aware of. So here he linked, Professor Berdichevsky linked in this work probability and entropy, because he looked at ergodic Hamiltonian systems, and therefore this eventually translates to or transforms to this work of Professor Berdychevsky, transforms into Einstein's formula in the limit, because these are all asymptotic, remember, so they approach other theories in their limits. So it approaches this particular work on thermodynamics and statistical mechanics, approaches the Einstein's formula of an infinite number of degrees of freedom, because that's for a continua. A continua has infinite number of degrees of freedom. Here we are talking about a random structure made out of multiple periodic structures, and therefore you have a finite discretization that is involved, very similar to what you do in finite element methods for structural problems. Same thing for the thermodynamic problem over here. So the corresponding theory became the core of his monograph. This was the other monograph that I was referring to. This is a 1997 monograph on thermodynamics of chaos and order. Chaos actually takes into account the issues that are there in the randomness, and order is that what you have in the periodic structure. So you should understand each of these separately and the correlation between them. And this was a book that he came up with in 1997, an English book, Thermodynamics of Chaos and Order. So many of your friends or classmates who are working on thermodynamic problems and propulsion related problems, you can suggest this book for them if they want to have a very deep and fundamental understanding of thermodynamics before they get onto their research. Many people are not aware of this wonderful monograph, Thermodynamics of Chaos and Order, 1997 book by Professor Berdichevsky. And statistical mechanics of ergodic Hamiltonian systems was applied successfully to the theory of turbulence. So again, for your classmates, the MTech students, classmates, or PhD students, classmates who are working on fluid mechanics or aerodynamics or gas dynamics problems, you can suggest this, especially if they are dealing with turbulence, because the theory of turbulence benefited from Professor Berdychevsky's work on statistical mechanics of ergodic Hamiltonian systems, and he himself applied it to the theory of turbulence. where Victor established the equations for averaged fluid motion. So again, see, periodic structure in a solid mechanics to a random structure in the reality of the solid mechanics problem. Same thing in turbulence. You are dealing with pockets of the fluid, each of which can be treated in within quotes periodic sense, and then you bring it into the randomness that turbulence brings. So you see that the way nature behaves, we have divided it into solid, liquid, gas, and all these things, but essentially their behaviors at the fundamental level are the same, because they're all made out of atoms, and the atoms made out of the same set of subatomic particles. So there is a common denominator that is going to all of them, and therefore fluid mechanics problems of turbulence can be understood from the randomness problems of solid mechanics as well. And Berdychevsky himself has made a huge contribution towards that as well, in establishing the equations of averaged fluid motion. And Professor Berdichevsky's major result in this particular area of fluid turbulence is a proof of the absence of universal equations of turbulence. Unlike many other fields where there's a universal equation, for turbulence you can't have a universal equation, and that absence was proved by the work of Professor Berdichevsky in the 1990s. And apart from that, and in that itself, of course, if you look at the changes of flow geometry, may result in changes to not only the boundary conditions, but also the governing equations as well. See, typically we are familiar with how the turbulence can change, or many of your fluid mechanics experts, you would see that they know how the boundary conditions change because of the turbulence. But the governing equation itself changes, and that's the beauty, and that's why you can't have universal equations governing turbulence. And that's the beauty of any unsteady flow that you have. And there are very good courses and experts on unsteady aerodynamics amongst my colleagues, and the courses that they offer might be of great interest to those of you who are interested in turbulence as well. The advances in turbulence theory were mostly based on Victor's theory of stochastic variational problems, which, as I said, he developed in the 1990s, in fact mid-1990s, when I moved to the US, and he moved out of Georgia Tech to Wayne State University. And this theory that he had on turbulence was also instrumental in the study of Kosterlitz-Thouless phase transitions and statistical mechanics point vortices. So there are point vortices in statistical mechanics. By understanding that, you can understand a field of vortices, and that's something that also benefited from Professor Berdichevsky's original work. He himself made the applications as well. And it has a great potential for future applications to statistical mechanics. So this is where he giving a room, the look forward that I talked about in Professor Hodge's work as well. The philosophy is same. So there are many potential, and it's a lying dormant treasure, a hidden treasure that both of these monographs of Professor Berdichevsky are. That just reading a few pages of it, you will get amazing ideas to build an entire career over it. So that kind of seeds are there in these books. So there's a large potential for future applications, in this case to statistical mechanics of dislocation ensembles. He is one of his favorite words, which he uses a lot when he talks, also is ensemble, because his family is associated a lot, his next generation, that is, with music, and therefore, the ensemble in a symphony, and he uses this word in engineering parlance also to refer to the dislocations also. The dislocations within a structure, a failing structure, those dislocations as a set are an ensemble of dislocations, and he understands the statistical mechanics of that and presents to us in this book and the papers that he's written after that as well. And Victor's study of irreversible thermodynamics. See, again, that's a very important area, which is a little more complicated than reversible thermodynamics, and Victor has spent a lot of time on irreversible thermodynamics as well, and it has resulted in establishing 3 new fundamental features of thermodynamic relations. And these are not important only for those people who are working on propulsion. It's as important for us who are working on structures, or for those who are working on aerodynamics. One is the fact that what is the fundamental feature of any thermodynamic relation, be it the first law, second law, as you know in thermodynamics, or the fallouts of that. Even prior to that, there's a fundamental feature of these thermodynamic relations, and the first one of them is the fact that they have a variational structure of only the reversible part. See, again, it's an irreversible problem, but it has a reversible part to it, and that is the leading order terms. Again, in the context of variational asymptotic method, you're trying to solve the problem in steps and asymptotically approach the exact solution. Similarly, the approach has come over here in terms of a variational structure for the reversible part, but for the rest of it, there is no variational formulation over there. That's why turbulence is so difficult to deal with, for example. So variational structure of the reversible part of the evolution equations, the thermodynamic evolution that takes place, that's the first one. The second great finding of Professor Berdichevsky in this area is the nonlinear generalization of Onsanger's relation. So those who are familiar with thermodynamics know about Onsanger's relation as some of the fundamental equations governing the thermodynamic processes, especially irreversible processes. So there's a possibility of nonlinear generalization of the Onsanger's relation, which are linear. And thirdly and finally, the law of decay of the microstructure's entropy. So the entropy can decay as well. It not only grows but decays. The law of decay of microstructure entropy in isolated systems. When you have thermodynamically isolated systems which are not having heat transfer with their environment in terms of the boundary conditions, in such situations there's a decay of the microstructure's entropy. So these are very, very fundamental findings, and although an expert in mechanics by training, Professor Berdychevsky obtained 2 results in mathematics also. I've talked about turbulence in fluid mechanics. I've talked about thermodynamics, the great contributions. I will probably conclude with 2 great results that he got in mathematics. First result that is very significant in the mathematical contributions of Professor Berdychevsky is that he found a new inequality in elasticity theory. So see, there are applications in physics and solid mechanics for the mathematical work that he has done also. He always gets that connection. He doesn't like pure abstract mathematics alone, leave it at that. Even if he does something like that, take it forward and see where it can be applied to a physical system. So firstly, he found a new inequality in elasticity theory, that the energy of any cylindrical, something like this that you see over here, any cylindrical elastic body that you have, the energy that is there in that cannot be smaller than, because inequality, that inequality sign is coming, it cannot be smaller than the energy of this body. So that basically says that the way people were computing this energy was by using the classical theory, right? Now, what is the classical theory? It's the Reissner's 2D theory. So the Reissner 2D theory for such cylindrical problems where you have a cylindrical shell. It could be a tube, it could be a pipe, it could be a shaft. In the case of aero applications where you don't go for solid shafts but you go for thin-walled hollow shafts. But as long as you have a cylindrical elastic body, and it need not be circular cylindric, it can be prismatic or any arbitrary combination, but it is continuing same cross-section throughout. That is what cylindrical means. So any cylindrical elastic body that you have, which means most beams as well, its energy cannot be smaller than, in other words, you're setting up the upper limit. So in other words, the lower limit. This is the minimum that you are setting up, and that minimum is is the energy which is computed by Reissner's 2D theory. Because for the same thin-walled hollow tubular shell, you can apply either a 2D shell model or a beam model, right? So, but if you're dealing with a beam model, you know that it's a lesser of an approximation or more of an approximation than the shell model, because already gone from 3D to 2D, now you're going to 1D. So it's good to have these inequalities, or which can tell you either the maxima or minima beyond which you can go, you can't go. So if you get an answer which is violating that, you know that you have done something wrong, and you can recheck the derivation. So we are saying that the energy of any cylindrical elastic body cannot be smaller than the energy of the body computed by Reisner's 2D theory in 1973. So that is a very important result. And the second mathematical result, which is of significance of Berdychevsky, of course there are many, but two most significant I would say, is that Professor Berdychevsky derived a new functional integral, asymptotics. So the asymptotics associated with a new type of functional integral that is crucial in stochastic variational problems. Professor Guru Prasad again not only works on dislocations, but lately he's been working on a lot of stochastic variational problems as well in IIT Bombay, and produced some great students and their theses and postdocs as well. So this work of Professor Berdichevsky is kind of a building block to that in terms of the new functional integral asymptotics crucial for stochastic variational problems. And he did this quite recently, 2008, relatively speaking, because we've been talking about his contributions over the decades. And he has also made a series of important mathematical advances in understanding something that many of you are familiar with, the Saint-Venant's principle. You know that the Saint-Venant's principle says that it doesn't matter how the boundary conditions are actually applied at any given end. Let us say in the case of an aircraft wing, what are the tip boundary conditions, what are the boundary conditions at the root where the wing is attached to the fuselage, and of course on the loads that are specified on the top surface, bottom surface, leading edge and trailing edge, etc. So whereas if you go to the interiors, that is immune to how the actual distribution is, as long as the equivalent distribution is the same. So if you apply an equivalent distribution, by which we mean the resultants are the same, then the interior solution doesn't vary, but the boundary solutions do vary, and how far they vary depends upon the cross-sectional dimension in the case of a beam, depends on the thickness in the case of a plate or a shell. Of that order of magnitude, you have to leave out the boundaries. So even if you have an asymptotically correct solution, it will not work very well, very close to the boundaries. And for that, you do need a three-dimensional model still. And there are ways in which the three-dimensional model can be interfaced with the one-dimensional or two-dimensional models. So basically, that's one of the other contributions in mathematics, which is crucial in understanding the Saint-Venant's principle itself from just a statement to its mathematical repercussions. How to actually utilize it in an engineering sense was something that was contributed by Professor Berdichevsky as well. So the quality, breadth and volume of Victor's work are striking, and they speak for themselves. Through his teaching, combining rigor, insight and fascination with science, Victor has helped generations of students to find their way in science. As blind men, we are lost, and these are people who come and open up our eyes and shine the light, so that we know where we are and we know where to go, and the best paths to reach that through an asymptotically correct approach using variational principles. And these optimal ways have been of great utility to many of us, his students, grand students, and great grand students as well. So, being a profound thinker on the fundamental level, Victor transmits to his colleagues an image of a real scholar, focused, dedicated, and uncompromising. And he's also known to his friends, and many of us students or grand students have become his friends over the years. All of us know him as a very warm and sincere human being. I talked about the humane nature of Professor Hodges also in my previous talk, and this is again another common denominator between them, because he intermixes impressive confidence. See, having confidence is one thing, but overconfidence, you can step out, blind confidence without perception. So confident yet perceptive. So Professor Berdychevsky is somebody whom we can learn practically how to intermix such an impressive confidence based on one's own dignity and the kind of work that he has made contributions for, with admirable humility. So many people see this as contradictions, but it is possible, and I've seen this with my own eyes in how Professor Berdychevsky and also Professor Hodges others live their lives. So, as I said, on the occasion of Victor's 65th birthday, about 10-12 years earlier, his former students and colleagues, including yours truly, we organized an international conference in his honor, and nearly 50 scientists from all over the world and a few students, of whom the 50 scientists were all his own students or co-workers, and we all gathered in Ruhr University, Bochum, thanks to the great host that Professor Lei was over there. I mentioned his name and his book earlier as well, Vibration of Shells and Rods. And this introduction that I'm giving to Professor Berdychevsky was also initially penned by Professor Lei, and with his permission I'm presenting it over here. And because he is somebody who has directly worked with Berdychevsky, rather than me, a second hand knowledge gainer from Berdychevsky, talk about him directly, like which I talked about Professor Hodges. I could, because I was directly a student, but with Professor Berdychevsky, I borrowed what Professor Lei told about Professor Berdychevsky as part of this particular conference. And that conference was a very emotional and memorable event for all of us, including me. I had one of my students who's now a professor at IIT Roper, Professor Shrikant Shekhar Padi, who accompanied me on that wonderful train journey from Italy, where we were staying for 6 months. We traveled through Switzerland and through a major portion of Germany to the northwestern frontiers of Germany, where this university is located in a beautiful spot. And we had a wonderful time with 4 generations of academicians over there. And evolving from those talks was a special issue, as I said, of the International Journal of Engineering Science. So I urge many of you to search for that and look at some of the papers which might be relevant to you. And this was dedicated to Professor Victor Berdychevsky, just like the conference or the Festschrift. The special issue of IJES was also dedicated to Professor Victor Berdychevsky, and it contains contributions of some of the participants of the Festschrift, including yours truly. And the co-author of that was another of my students, who is now a professor at Shiv Nadar University, Professor Ramesh Gupta Burela, who works in the Mechanical Engineering Department of Shiv Nadar University today, and is making immense major contributions. He has done pioneering work on hyperelastic materials, which kind of became the building block for Kaja's work as well, his codes as well. And so that work of the NM cadet is something that I would bring to your notice as well. So with this, I'm sorry I took half an hour more, 35 minutes more than the usual class timings, but when I'm talking about Hodges or Berdychevsky, and especially their contributions to mechanics and mathematics, I just lose my sense of time, and the result of that is a longer class today. So thank you very much. I really appreciate. I hope a few of you are still around in the class, and if any of you have any questions or doubts, I would be happy to answer, and we will take it forward in the next class from there. Thank you.
मृत्युंजय मंत्राः
त्र्यंबकं यजामहे सुगंधिं पुष्टिवर्धनम् उर्वारुकमिव बन्धनान् मृत्योर्मुक्षीयमामृतात् एते सहस्रमयुतं पाशा मृत्योर्मर्त्याय हन्तवे तान् यज्ञस्य मायया सर्वान् वयजामहे मृत्यवे स्वाहा मृत्यवे स्वाहा